you very much. Before I forget, it was where Simone Marchesi. And with this, I should start saying that this is a work we started many time ago. Our scope was to understand in general what a regular sheaf is. Everyone agrees about regularity in the projective space, and for other spaces you have different definitions. So we try to find good properties for regularity, and once we understood the nice properties for regularity, we realized that they were equivalent to a definition already given by Costa and Mirò-Roig. So we were really disappointed because we spent years and years trying to write the right definition. But we realized that we can use exactly, well, apparently a completely different definition, and it's equivalent. And with this other point of view, we were able to do much more than they did with their own definition. So this is what I'm going to spend today. But in order to understand what regularity means, I prefer to start recalling, and maybe it will be a half of my talk, recalling regularity on PN, but with a point of view which will be exactly the point of view that we will use for our definition. So I start regularity. Yeah. And let me start with an exact sequence. What it is. But here you have a qualification that's important in different way. Here take some space here, here, right? Okay. So this will be the main exact sequence. I will going to start. Maybe you recognize this. This is just taking sections from O1, and you have a long exact sequence for exact sequence. But this in irregularity, by definition, you have a sheaf is regular. What you impose is that the cohomology groups in this order 0, here you write when the tensor is with F, so and here, and well, here you should have -1. This is the definition. This is the classical Manco-Castellovo regularity for a sheaf, and I want to write down the properties. Of course, you can realize that if you tensor this with F, automatically what you get is the conditions such that the kernel here tensor with F is 0. So the first property is that if you get the multiplication map here, I report that is a first one is such space. The property is map, this is subjective. So this is immediately taking the commodity here after tensoring F. So this. The second property is that anytime you have that regular, well, in these properties, I'm assuming that it's regular. So once F is regular, you get that extension of one regular. And this is also very easy to prove, but these properties I want to keep, so I sketch proof of the properties here. The only thing you have to do, you need to take the vanishing, to put it on this vanishing. And the only thing this is your hypothesis, this is 0. So you need to prove the same here. And the only thing you have to do is to write here to transfer B with F minus 1. So you get here this, continue. But one, two, so on. And this H1 is between this H1, which is 0, and H I plus 1 of this, and this H I plus 1 is between this, which is 0, and the next one, and so on. So you immediately get this. The next interesting property is that you evaluate sections. It is objective. So I'm saying that F is globally generated. And the way of proving this, what you know is that maybe F is not globally generated, but you know that if you take a very high twist, it is globally generated. So in order to prove this, 2, 3, you know that this is globally generated for M enough, and this means if I write here, you can see. So this means that you take sections, then O. This is objective to F of N, but instead of writing F of N, you write here N. So you have this is objective, and enough. And you can use property 2 and consider the multiplication map. One space of N. And you have that this is objective with N is at least 1. Because you know that F is regular, so everyone is regular, and so on. So F n minus 1 is regular as long as N is 1, so this composition is objective. And on the other hand, here you can write the same H. And now you collapse these 2, and you get here O 1. And
would you please wipe with the cloth because it's difficult
sure,
to see what is there.
So this is objective, so this is objective. for M at least one. So when you have this map is surjective for this M, you get exactly the same property for M minus 1. So you go backwards. At the end, you arrive to the case N equals to 1, and this is exactly the case you wanted. So this is the proof. And here you get the main point. The main point is that you can find a resolution from the side of n number of n number of times not in. Before sketching the proof of this, let me tell you that this is the main point. In fact, for my surprise, I realized of this many years ago that that was the starting point with my work with Simone. And I was commenting this, and it seemed that no one knew that this was true. And in fact, this is a characterization. Once you have an F that fits resolution like this, you take homology and you obtain immediately these conditions. So this is a characterization of regularity. So our point of view is to define the regularity not in terms of homology, but in terms of resolution. So regularity should be that the sheaf has a special resolution, that we decide which one we want. That's the point. And for the proof of this, let me sketch the proof. What you do, the first part, you have this property 3. You have that the number of times you have exactly this dimension, you have a surjective mass. So you have a number of times, this is surjective, and you have points. Right. Okay. And what happens to this new sheaf is that you transport the vanishing from F to the vanishing this, and you get and now one. You can, in principle, you can only use H1 and arrive at H2. H2, so all these are 0. But observe that here, exactly what you are taking is a knot is exactly the space of section. So when here you take it's not, you have an isomorphism. So in fact, you get two more conditions. You get one. Also, this is 0. And this is also 0. So in fact, with this, what you are getting is that F1 is regular, and you get an extra condition. So doing like this, you start with F, now you have all knots with kernel, and you can repeat exactly the same. This is regular, so again you get some surjective map here, and you get a kernel exactly with the same properties as I said. So you can write here all in the line 1, and here what you get is F2 of -1. And now the property you get for this is again you get it's not F2 equal 0. You knew that this H naught was 0, so you translate this here, you get also that this is 0. And again, now you get that F201 is regular, so now you have O minus 2. Something, you go backward, and you write some F n 1 minus n 1. Yeah. Some O minus n. And in for this, what you get, if you start to translate everything you have here, you have 0 equals. It's not n. 1 equals H1 1 1. Here you are just translating all the conditions you get here, and you arrive to this other condition. You have all these vanished. So with this, we are saying that Fn plus 1 is generated by its global sections. But how many sections you have? No sections. So automatically, this implies that this is just like this. So you get nothing with this last kernel, so you get the wanted solution. Okay. So as it said, this is the important part. And everything comes from this example. And this is what I want to analyze and see exactly which kind of long exact sequence we want. And
Sorry, when you conclude that it was 0,
yeah.
I mean, it doesn't have sections.
This is globally generated because it's regular.
Yeah.
It is generated by its global section, but it has no section. So, I mean, you have a projective map, and this is 0.
Okay.
Okay, so this resolution you can consider as an extension of length n. But this is the same as n you want. Yeah. But in this is the canonical. So this is a one-dimensional step. This is just duality. So what happens is that on Pn you have a natural extension here, and one representative is this one, and it seems that this works. So the point is on a general variety, because this is always true, just try to find a natural extension of omega. Another observation is that being regular, once you have this model, the regular is saying that it's equivalent to saying that F has a resolution exactly as the one you got here. So your goal should be on any variety to find a natural extension here. In regularity should mean to have a resolution at the sheaf that you have on the right. Another property, well, it's possible. I can write it here. I want to recover this. Is that the elements in the resolution and in fact any twist. The point, because this is going to be very important, the important part is not only to use this to prove this, we need these exact sequences plus twists. So here I'm considering exactly the vector bundles appearing in the resolution, but I can take any twist and the proof is the same. These n plus 1 line bundles generate if you know what the desired category is, get the desired category, or the rotating group, if it generates this category, it generates this group. And well, if you don't know what these objects are, the point is essentially that well, first, in anything generated by this, in any of these cases, if you have this element, and this element, if you have an exact sequence like this means that they generate in particular over 1, and twisting everything by 1, then you get that you generate over 2, and so on. So you generate all possible line bundles because you can go backwards. Also, because if you tend to be minus 1, you have this generator, so you generate also O minus n minus 1 and so on. And once you have all line bundles, you know that you are done, because well, you can do without doing this, because but it's also interesting that but I will go back later on. Another interesting point, well, maybe I start to run out of page. Make some properties here. So, if I want to obtain all line bundles on Pn, I got them. I mean, I'm using, for example, here O minus n minus 1. As I said, that this is the canonical bundle. If I tensor this with the canonical line bundle, then I get this, and so on. And for example, if I want to obtain over 1, I can tensor the anti-canonical line bundle, and I get this. So if I take, or you want to send the set all possible line bundles, is obtained by twisting with multiples with 1. of the canonical function. And you know that property, there is a very celebrated theorem for line bundles on the end, which is Horrocks Theorem. That S is not free, that F is a direct sum of bundles, even only if it has no intermediate cohomology. In tensor with any volume. Bundle is 0 for Q 1 to n with 1. And so the point is that you can characterize length bundles in terms of tensor by length bundles. In the proof, it's also very simple. What you do, well, of course, one implication is trivial. If you have a direct sum of length bundles, they have no intermediate cohomology, so that's okay. And vice versa, if you have sheaf without intermediate cohomology, you take M small. Regular. By the way, I'm going to use this later, so before I forget, by definition, you say that is irregular. So irregular means that F twisted by N is regular. And while you have this, you recall the definition of regularity. It involves intermediate cohomology. So you're assuming that F has no intermediate cohomology. What you have is that necessarily, since you're assuming that F n minus 1 is not regular, then necessarily n, small letter, small, so for the dimension, n minus 1 n is different from 0. And this is the same by duality. Here again, you get the canonical value. So we're saying that M2 minus n is different from 0. And in fact, what you're saying? On one hand, you're saying that F so n is globally generated, because we don't have this objective. But this is saying that you have a non-zero model. Is the dimension of the space of morphism from M to O. So automatically, this implies that this composition is different from 0. So this is saying that O should be a direct sum of this, so necessarily O minus N. Yes. So you get a direct sum, and you apply induction on the right. It satisfies exactly the same condition. It has no intermediate cohomology, so you can. And finally, you have the analog of
what in algebra is called hyperspecificity
theorem, which means that so any f has a resolution like this, where each pi is what is called in arithmetically
Roman
sheaf, which means that it has no intermediate homology, or by Horrocks theorem, another sum of so officially the definition is one, but Horrocks theorem is saying that's the equivalent of unitary number. And the proof,
I don't want to spend more time.
in this case, essentially, what do you do? Now we cannot use regularity or anything. We are going to use directly Horrocks theorem. We start with some F, and we pick the smallest. Here I can explain proof. So we start with F. So you take the smallest twist with section. So in principle, you will write here M, but you write it here. So you take the number of sections it has. But probably with this, you don't generate all the sections of M plus 1. So maybe you need to add something else. And then you get a subjective map to F tensor with M plus 1 or M plus 2. If you don't have enough sections, you add sections, but at the end, you complete V naught. And since you are constructing this in such a way that taking H naught is surjective, what you get here as a co-kernel is something without H1. So this has a property that H1 L is 0 for L. You repeat exactly the same for this F1, and you get here some F2 with no H1 and with no H2 because of this, and so on. And you go backward, and if you arrive to the last kernel here with an intermediate homology, you can prove that it is locally free for homological dimension is by Horrocks theorem. The last kernel you get here is again a very sum of like values. So these are the main points. So now let's try to repeat this in other spaces. So now I need to try to construct a big diagram. What I try to explain it a little bit. So let's try for Pn cross P. Let's try to, as I told you, the main point is to find something similar to this star. So of course, one possibility is just to start with. Well, let me write here O n Ij, meaning the pullback of I here and Oj here.
A little bit lower because with the light.
Okay.
was okay. And the left was okay.
This will mean the tensor product of the pullback of y here, pullback of j. So I can try to use this for Pn, for example, but I want to be sure that I do something like that. So I take this to give Pn, take the pullback, so maybe I have more space here. So the pullback of this should be right here, 0, 10, but maybe you agree that if I write 10, this is not symmetric. So I write here 1. So I take the pullback of this of Pn, and I do tensor with 0, 1. So here I will get 1, some number, which is not important. So let me write the star meaning some number of -1, some number, and we will finish here with -n1 for some number, but this number is 1. And now I can repeat exactly the same for the pullback of star particle on Pn. So I will get, so here -n is fixed, then I get 0, of -n, -1 number, so on, of n, and here the number 1. And I get this, I compose, and now I have an extension. And this extension, where is limit? Because with this extension, I will get, as I did for this extension, something with O minus n minus 1, which is the canonical. Pn minus n minus 1, which is the canonical. Pn, so I will get a canonical. But still, this is not symmetric. I started with Pn and then with Pn. I have a possibility, and the possibility is to compute this. I know that here I can repeat exactly the same, but instead of using -n here 0, and here we get 0, some number, 0.1, some number, of 0, and now with some number, because it's just there with number of times, so on, I can do exactly the same here, and here we have something. And there is a trick I can use, which is called the mapping cone. I have to repeat it many times, because with this, what I get is a commutative diagram. And with this, I can get a resolution starting with O and N, and finishing O 1, 1. And what is what I get? What I get is exactly what I get here in this direction, except in the border. So here I will get O, some number. In the next step, I will get O minus 1, 0 plus O 0 minus 1 number. The same here, O minus n plus 1 number plus O minus n plus 1 n, it's a number, so on. And in fact, in the middle,
This is the total complex, right?
hmm?
This is the total complex.
Yeah. So at the end, in the middle, what I get is over J, a number with a property that is J. 0 and the sum. R. This is the in the R. In, well, so this is saying that if this is going to be the analog of my exact sequence. Let me try to convince you that this is something natural in the n cross p. How many elements do I have here? Exactly as many elements as I have in the two ring in correlation R. The generators here are I is 1. I, J, H1, H2 are the hypotheses in P. Yeah. So the elements I get here are essentially in a natural way in relation with the two ring of P cross P. Here, what I got is at a step one less value because for the two ring of the projective space, what I get is just one generator, which is a multiple of the hybridization. In fact, here I get this answer, K, square, and so on. So this is what I want to obtain. And at this point, it is saying that the kind of resolution I have to look at, they don't necessarily contain only one vector bundle or line bundles at the place. Maybe many, and depending on the show rate. And on the other hand, if I repeat the trick of tertiary with multiples of the canonical bundle, I will not get all possible in bundles, only few of them. So let me write down briefly regularity, using derived categories. This is what was done by Costa and Mirò-Roig. So the first step is that when you take any x of dimension n, you will define what is called a block, and the block is just to give a collection of collections of vector bundles. So each I consists of vector bundles. For each I, you have a different number. With some conditions, write the condition. I can define in general what is called a helix, just saying that I define a as the collection I have here, tensor with omega, one. And with this rule, I can define for each I. Collection. Now I have one possible integer. This means, of course, that any of these you tensor with a bundle. And let me cheat a little bit. Which conditions you have imposed to these vector bundles? Well, the condition should be that you have no extension. J prime. This is 0, in which cases? But looking at Horrocks theorem, it will be true for any intermediate cohomology. When Q equal to 0, so when I'm taking homomorphisms, the condition is that I have no homomorphism from something on the right to something on the left. So this is prime and except, of course, homomorphism. One vector bundle itself, it should be just the endomorphism. And dually, okay, the condition will be writing maybe way. This is 0, and this is 10. Except at n j and j. Okay. So with this setup, what they get? What they get is the following. We have one thing, just looking at the things that, as I said, now any n+1 consecutive elements like this generate the derived category. Oh, by the way, they put as a condition that is generate the derived category. And once you construct what is called a helix, then n+1 consecutive elements generate the derived category. And with this definition, they give a regularity definition depending on the elements. Well, now they define irregularity, which is the analog of, because what you want now you don't have it. You can take twist, but elements in the helix, they define regular bits. This is a strange condition because depending on this, but not on elements of this, but what is, it's not important the definition, because what I'm going to say. How much time do I have? Because I started a little bit late.
Yeah, 5 minutes more.
5 minutes, okay. I try to. Okay. With all this definition, what they prove is that irregular implies regular property. If they prove that any n+1 check regular, okay, but anyway, the point is the following. With all this set up, the important part is that you have the helix with some homological condition is the important thing is that you have a solution using this. That oh no, the important part is that they prove that irregular implies, and in fact it is equivalent, and they didn't prove that, but you can prove that this is equivalent to have a resolution exactly as you want. So this is right not and and so each of them, let me write this as some a I. Some vector. This means that here in this part of the block you have vector bundles, and each one has an exponent. And the important parts are they don't prove it explicitly, but in particular, you apply this. These vector bundles, you get the analog of each of them as a resolution like this, and one, and you finish with the same one, and recall that this is nothing but human n one copy. And this is exactly for field of each block, the analog of this exact. So the point is that now you can try to repeat exactly everything. So now assume that you don't know what the category means. I don't need to assume that because this is true for me. And try to do exactly the same. take X, you need to assume that this is random. I will tell you why. And you take H, some collection of vector bundles with this condition. Rows, the condition that this you impose as condition that there exists exact sequences like this, and you impose also, I erased, they were here, plus homological condition. The writer, the one I wrote here, knowing the mean homology and so on, and that's enough to repeat absolutely everything. You have this and all its tweets, which are exactly these exact sequences, and you can repeat exactly all these things, exactly the same proof. But the important part is that you get this objectivity for any irregular shape, where here what you need to write is the direct sum of elements of A minus M, and so on. And you get exactly with this that having a resolution like this, so you have now that the solution of F in the term we want, so like this, is equivalent to, and this is the right definition, right? Let me put it in a compact way. It's Q and the and Q 0. The solution is starting with elements in the D minus L. So this you define as embedded. And with this definition, so you can repeat absolutely everything. You get, and this is the most important part, this is essentially the new part, because if you realize, I finished here with this comment. That you can repeat absolutely everything, also Horrocks theorem. And then you can define your own notion of ACM. ACM again means that you have a direct sum of elements on the helix, and this is equivalent, well, because of the homological condition, this is equivalent to have no homology when tensoring with all possible duals of all elements in the helix. So this is something essentially new, and it avoids all these problems of trying to study wide varieties, because now it is in fashion to study a variety depending on how many vector funds, ACM vector funds you have. You have a huge family, this is called a wide variety, and so on. From this point of view, then anytime you have a helix like this, you can define your own notion of UCM and of course there are many open questions. How many pattern varieties? Pattern is important because if you recall here for the proof of this, we need that for a sufficiently high twist we got globally generated. So now we need that for a sufficiently high twist of the anti-canonical bundle. You have some properties, so you need the anti-canonical to be positive. So this is why one. But the point is that with our definition, the regularity is equivalent to having such a resolution. So in fact, our definition coincides with the definition of Costa and Mirò-Roig. But now we can prove much more results. We have Horrocks Theorem, and from Horrocks Theorem we can try to obtain some new results. I'm out of time, so I have a couple of sentences prepared, but I think it's better. So here, of course, still we try to do something different from Laura and Maria. The point is just to try to relax the condition. We have a lot of examples of cases with properties. We get a desired resolution. They don't fulfill all of these conditions. I think I talked too much, so I stop.
Questions? I have a question, but I don't know. Does it make sense to try to do these things for a triple product of things? I mean,
yeah, in fact, for products of projective space, everything is okay. In fact, I said at the beginning that everyone agrees on the definition of regularity in projective space. Anyone agrees on the definition of regularity for any product of projective space. When you write to Riemannians or quadratic and so on, you get many different definitions. But now we realize that the right definition is essentially the definition of Laura and Maria, but realizing that you can do it in terms of a helix, not in terms of right mutation and so on. In fact, they gave the definition because they know values on spectral sequence, and this is exactly the definition for which you get such a resolution. So you get right mutation because you have a collection, you have a dual collection, and essentially this is done in terms of the dual collection. But sometimes it's better to be an ignorant. So, I mean, I never understood your categories. I know how it works. This is not a network definition. I will never define it, even know what I know. I don't think it's necessary for anything in my life. So we try to reproduce the original techniques in the projective space, and it works. And I don't know whether fortunately or unfortunately, our definition coincides with the definition of Laura and Maria. With this other definition, we can do much more things.
No questions? Then thanks, Enrique, again.